This is Dr. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the interfacing of memory of different sizes of RAM and ROM with 8086 microprocessor. The slides are prepared by referring the textbook Advanced Microprocessors and Peripherals. Authors are K.M. Budchandi and IARE, publication McGraw-Hill. The problem statement is interface two 16K by 8 EPROMs and two 8K by 8 RAM chips with 8086 microprocessor. Select suitable address maps. So in the problem statement, they are given with two 16K by 8 ROMs and two 8K by 8 RAM. So for any memory, if it is given with A cross B, A indicates the number of memory locations and B indicates the size of each memory location. So now in this case, here we have A number of memory location and each memory location size is B bits. Each memory contains 2 power n memory location where n is the address lines. For accessing the memory, we are going to give some address. If this address is n bit size, it is going to consist the number of memory locations are 2 power n memory location. The relation between the number of address lines and the number of memory locations is, if the number of address lines are n, then the number of memory location we access is 2 to the power of n. Each memory contains 2 power n memory location where n is the address of chip. Next, each and every memory location is consist of m number of bits. This will decide the size of data bus with m number of bits. Either the data may be transferred to the memory or retrieving from the memory. Read-write permission from the memory. So that's why I have kept the data bus as bidirectional one. Each memory location contains m bits, where m is the number of bits in each memory location. The entire chip will contain, total memory locations are 2 power n. Each memory location contains m number of bits. So the total number of bits contained in the memory chip is given as 2 to the power of n into m bits. Let us consider a 8K by 4 memory. Here it indicates 8K is the number of memory locations of this memory block is 8K. The size of each memory location is 4 bit size. For accessing any memory location, the address lines which we require are n. So for finding out the n value, the number of memory locations we are going to be represented as 2 to the power of n value. So from this we have to find out what is n. So the number of locations given in the problem are 8K, where 8 we can represent as 2 to the power of 3. 1K is equivalent to 2 to the power of 10, which is equivalent to 2 to the power of 3 plus 10, which is equivalent to 2 power 13. It specifies the 13 address lines are required for accessing any memory location of 8K by 4 memory chip. Coming to the problem, interface two 16K by 8 EPROM and two 8K by 8 RAM chips with 8086 microprocessor. Select suitable address lines. So first we will say the RAM address space, how many number of address lines are required, we will compute. In the problem given, the size of each ROM is 16K and consider two RAM chips ROM 1 and ROM 2. Each of size is 16K. So the total size of this ROM block is given as 16K plus 16K, which is equivalent to 32K number of memory location. For finding out the number of address lines are required for accessing the memory, we will represent this is as 2 to the power of n. From that we can find out what is n indicates number of address lines. So the total ROM size is 32K, which we can represent as 32 as 2 to the power of 5 and 1K as 2 to the power of 10, which is equivalent to 2 to the power of 5 plus 10 gives 2 to the power of 15. So for accessing any one of the memory location of given ROM blocks, the number of address lines are required are 15. 15 address lines are required. In the address space of 8086, the number of address lines we are having is 20 in number, starting from A0 to A19. Out of these 20 address lines, we require 15 address lines. So we are going to select from the lower one, that is A0 to A14. So A0 to A14 are the number of address lines are required for accessing any one of the memory location of the given ROM blocks. Coming to RAMs, in the problem they are given with 2 RAM chips, RAM 1 and RAM 2. Each RAM size is 8K size. Our objective is to find how many number of address lines are required for accessing any memory location of the 2 RAM blocks. Each of the RAM contains 8K locations. So size of each RAM is 8K given with 2 RAMs. So the total size of 2 RAMs is given as 8K plus 8K, which is equivalent to 16K. The objective is we need to find out how many address lines are required. For finding out the number of address lines, the total memory location we are going to be represented as 2 to the power of n. So 16K we can write as 16 as 2 to the power of 4. 1K is equivalent to 2 to the power of 10 in total, which is 2 to the power of 14. 10 plus 4, 14. So 14 address lines are required for accessing any memory location of the given 2 RAM blocks. These 14 lines we are going to be take from the LSB bit out of A0 to A19, the 20-bit address space of 8086. From A0 to we are going to take 14 address lines, that is A0 to A13. So A0 to A14 for accessing ROM, A0 to A13 are for accessing RAM block. Now for finding out the address mapping for RAM, in the given ROM blocks, we require 15 address lines, that is A0 to A14. From A0 to A14, this address space is required for accessing any memory location of the ROM blocks. For each and every bit, we can provide the value as 0 as minimum value by assigning each and every bit as 0, and the maximum address we will get by providing each and every bit as 1. Because if I have 2 address space A0, A1, starting address will take as 00, 01, 10, 11. So the minimum address generated by passing each and every bit as 0 in the address space. The maximum address we will get by giving or by assigning each and every bit as 1. So the address here it is 0, 1, 2, 3. Now coming to the given 2 ROM blocks, the minimum address we will get by providing each and every bit as a 0, 111 as maximum address. The lines A15 to A19, these are used for decoding purpose. For accessing the memory, A19 to A15 are not required. So those address lines we will use for decoding purpose. Now we will see the address mapping for given RAM blocks. As per the problem statement, the number of address lines which we require are 14, that is A0 to A13 address lines. So from A0 to A13 address space we will take for accessing any one of the memory location of 2 RAM blocks. The minimum address generated by providing each and every bit is equivalent to 0. The maximum address or the last address we can get by assigning each and every bit as 1. By combining the address space of both 80 RAM block and ROM block, we will get, this is the address space which we require. For ROM, we require A0 to A14. For RAM, we require A0 to A13. Now here, whatever the address space which we are having for RAM, the same address is given for ROM also. So for differentiating whether it is RAM address or ROM address, whatever the maximum utilized space is there, beyond that we are going to be select 1 or 2 bits depending upon how many chips we are having. So now in this case we have only one ROM section, one RAM section, so we require only 1 bit. So till A14 the address lines are required for generating the address, either it may be ROM or RAM. So till A0 to A14 we can't take any address bit for differentiating ROM and RAM. So for that we will take the next bit which is A15. The next bit which we will take as A15. By assigning 1, we will access a ROM. By assigning this bit as 0, it indicates for accessing RAM. What about A14 with respect to RAM block? Because for RAM we require A0 to A14. For RAM we require from A0 to A13. A15 we are using for differentiating either it is a ROM or a RAM block. How about A14 corresponding to RAM? So the A14 value for RAM is a don't care. Either we can assign this one as 0 or we can assign this bit as 1. Because A14 will not signify any memory location or differentiating the ROM block and RAM block. So A14 for RAM we can assign with either 0 or 1. For getting consecutive memory location, it is always advised to take this one as 1. So in this example, I am taking A14 as 1 for a RAM block. Now the address which we are going to get for ROM and RAM as follows by omitting A16 to A19 for decoding purpose. In the hexadecimal, we will get by combining 4 bits as 1 hexadigit. The first address is 10008 0000 0 0000 0 0000 0 1111 F 1111 F 1111 F 1111 F. Next for RAM, the starting address will get as 0100 which is 4 0000 0 0000 0 0000 0. The maximum address for RAM is 0111 as 7 1111 that is 7 F 1111 F 1111 F. Now if you take the difference between the maximum address to minimum address, it will specify how much amount of memory it is there for RAM as well as for ROM block. Now coming to the address lines A16 to A19, what is the value we have to pass? Here we have the number of address lines are left out for decoding purposes: A16, A17, A18, A19. These lines are used for decoding purpose or for enabling the chips. we can use these address lines. So as these are 4 bits and they are don't gets, either we can pass these bits as 0000 in the hexadecimal to binary format to 1111. Total 16 combinations you'll get. Out of the 16 combination, we can select any combination. It is not mandatory to give a particular address for RAM and ROM as same. For A16 to A19, the user can go for any configuration. Out of this 16 combination, either they can give any one combination for ROM and one combination for RAM, or ROM and RAM will given for the same combination. From A14 to A0 are required for ROM block, A13 to A0 are required for RAM, A15 we are using for differentiating whether the address is for a ROM block or RAM block. Now when we restart or power on the 8086 processor, the CS and IP values will generate as FFFF0H. So out of the address lines, A16 to A19 are used for decoding purpose for enabling the memory chips. After reset or power on, the CS and IP will initialized for the address FFFF0H. So as this is a initialized memory location whenever a system is started, so this memory location we want to assign for ROM as bootable programs are stored in ROM. If you observe the upper side, it is consist of FFF, indicates the upper bits are 1111. How many bits are left out? It is better to give as 1111 for the ROM address. So here each and every bit from A16 to A19 we will assign one to assign the address FFFF0H for ROM location. So by giving the address as 1111 for ROM block, how about RAM? So for RAM, either out of the 16 combination, we can go for giving any combination. For getting a continuous memory location, here I am selecting here also all the bits as 1111. So whenever the consecutive memory locations are assigned for a ROM and RAM, the access of the memory will be at faster rate compared to a different memory location. Now this address space we will represent in hexadecimal representation by grouping 4 bits as one hexadigit. The starting address for ROM or minimum address for ROM, it is given as 1111, which is F, 1000 as 8, 0000, 0, 0000, 0, 0000, 0. The maximum address is 1111, F, 1111, F, 1111, F, 1111, F, 1111, F. So this is the address space which we are assigning for ROM blocks. Whereas for RAM, the starting address is 1111, which is F, 0100, 4, 0000, 0, 0000, 0, 0000 as 0, and the maximum address or the last address for RAM is 1111, F, 0117, 1111, F, 1111, F, 1111, F. So this is the address space which we are assigning for RAM. If you observe these address lines, these addresses are continuous, so that the access speed will be more. So the address space for ROM is F80002 FFFFH, F800H2 FFFFH. This is the address space which we are assigning for two 16K by 8 ROM blocks, and the address space F40002 F7FFF. This is assigned for two 8K by 8 ROMs. The address space is F4000H to F7000H. So now in the memory block, the starting address for RAM, it is given as F4000H to F7FFFH. This is the address space which we are assigning for RAM. And the address space, the next memory location is F8000 to FFFFH. This is the address space which we are assigned for ROM. So this address space, whenever we are assigning, we are considered two cases. One is assigning the address FFFF0H for ROM. So if you observe the ROM address space, this address is lies for ROM. The second point is consecutive memory locations for memory chips, that is ROM as well as RAM. So from F4000 to FFFFH, till that point we are going to take a continuous memory location. So the access of the memory will be at faster rate. Now we will arrange the memory blocks as in the problem statement. We are given with two 16K by 8 ROM blocks. This I'll take as block 1. The second block, that is 16K by 8 ROM block, as block 2. 8K by 8 RAM block as block 3. 8K by 8 RAM block as block 3. The two 16K by 8 ROM and two 8K by 8 RAM are arranged in parallel to obtain 16-bit data. On one side, that is right hand side, whatever the memory blocks are there, this we are going to be take as even address memory bank. On left hand side, whatever the memory chips we have placed, it is for odd address memory blocks. For differentiating, either address provided is even address or odd address based upon A0. The LSB bit, if it is equivalent to 0, it indicates it is an even address. If it is 1, it is odd address. So if A0 is equivalent to 0, the address is even, then a lower memory chips is selected, which you have placed in the diagram on right hand side for 8-bit data transfer at even address. If A0 is equivalent to 1, the address is odd, then the upper memory chips or odd address memory chips will be selected for 8-bit data transfer. If it is 16-bit data transfer, both even address and odd address will be accessed. Next, for indicating either the size of the data is consist of upper 8 bits or not, that will be decided by the signal BHE bar, bus high enable, which is active low signal. If BHE bar is active, that means BHE bar is equivalent to 0, the signal is said to be active, and the upper memory is selected, which is placed on the odd address memory bank. Indicating 8-bit transfer at an odd address with combining A0, it will decide whether it is 16-bit data transfer or 8-bit data transfer. Now we will see the address lines which are required for selecting any one of the memory bank chips. So now if we see this arrangement of ROM blocks and RAM blocks, if the data is 16-bit size and if it is corresponding to ROM, we have to select or we have to enable both memory chips block 1 as well as block 2. If it is 8-bit, either we have to select block 1 or block 2 if it is corresponding to ROM address. Based upon the address, if it is even address, we are going to select the block B2. If it is odd address, we are going to select the block B1. If it is 16-bit data transfer corresponding to RAM memory, then the block B3 and B4 we are going to be enable or select for data transfer. If it is 8-bit and from odd address, then we are going to enable the B3 memory chips. If it is 8-bit data transfer from the even address, then we are going to select the memory block B4. Now the address decoding mechanism for selecting the chips will be decided by the 3 lines. One is BHE bar, A0 and A15. Whenever A15 is 0, it is corresponding to RAM address. Whenever A15 is 1, this is corresponding to ROM chips. The size of data will be decided by A0 and BHE bar. If A0 is 0 and BHE bar is equivalent to 0, it indicates we are taking a 16-bit data transfer from both even and odd address space. So the data transfer is even and odd address in RAM. That is word transfer, that is D15 to D0. If A0 and BHE bar is 01, then it is a 8-bit data transfer. If you observe A0 is 0, it indicates it is even address space. And BHE bar is 1, that indicates it is lower 8 bits. So whenever A0 BHE bar is 01, it indicates the data transfer is only from odd address in RAM, that is byte transfer on the lower bits D0 to D7. Right? When A0 is 1 and BHE bar is equivalent to 0, then it will indicate it is a 8-bit data transfer. By observe A0 as 1, it indicates it is an odd address. As BHE bar is equivalent to 0, it is upper 8 bits. That is on the data lines D8 to D15 we can have the data. The data transfer is from or to only odd address in RAM. That is for byte transfer from the lines A D15 to D8. Now coming to ROM case, whenever A0 is 0 and BHE bar is equivalent to 0, it indicates it is a 16-bit data transfer for RAM chips. So for this, the data transfer will be takes place from both odd and even address space or memory chips. It is a word transfer from D0 to D15. When A0 is equivalent to 1, BHE bar is equivalent to 1. However, it is corresponding to ROM. By observing A0 as 0, it indicates it is a even address bank, and BHE bar is 1. That means the data is present on D0 to D7. So the data transfer here it is taking to the memory or from the memory is only from even address in ROM, that is byte transfer from the data lines D7 to D0. The next combination is when A0 is equivalent to 1 and BHE bar is equivalent to 0, it indicates it is also a byte transfer. As A0 is equivalent to 1, it indicates odd address, and BHE bar is equivalent to 0, it indicates upper 8 bits. So the data transfer it is taking place only from odd address in ROM, that is byte transfer on the line D15 to D8. The combination A0 is equivalent to 1 and BHE bar is equivalent to 1, this is not used for data transfer. No data transfer will be takes place when A bar is equivalent to 1 and BHE bar is equivalent to 1. Now for selecting the memory chips, we will design a decoder which is a 3 to 8 decoder. First we will see the functionality of 3 to 8 decoder, then we will apply this decoder for decoding purpose, which are the address lines are required. So for this 3 to 8 decoder, the address lines which we are giving here it is A2, A1, A0. Based upon A2, A1, A0, the output lines from Y0 to Y7 will be enabled. So in this example, I considered all the signals are active high signal. So whenever you have passed the address information on the lines A0, A1, A2, one of the output line will be active, that is 1, and the remaining output signals are inactive state, it will possess 0. When A2, A1 is 0, 0, 0, Y0 will be enabled and the remaining Y1 to Y7 are disabled. When A2, A1, A0 are 0, 0, 1, Y1 will be enabled, Y0 and Y2 to Y7 output signals are disabled. The next input combination or address lines is 0, 1, 0. When we pass A2, A1, A0 as 0, 1, 0, it will enable Y2 signal and Y0, Y1 along with Y3 to Y7 are disabled. The next address combination is 0, 1, 1. When it is 0, 1, 1, Y3 will be enabled from Y0 to Y2 as well as Y4 to Y7 will be disabled state. The next address is 100. When it is 100, Y4 will be enabled. From the address or output signals Y0 to Y3 will be disabled as well as Y5 to Y7 will be disabled. When we give the address lines input side as 101, it will enable Wi-Fi output signal and the remaining output signals, that is from Y0 to Y4 and Y6, Y7 will be disabled. For the input combination on the address lines A2, A1, A0 as 110, it will enable Y6 output by disabling Y7 and Y5 to Y0. For the last combination, that is 111 on the lines A2, A1, A0, it will enable the Y7 output line and by disabling Y0 to Y6. This is the functionality of 3 to 8 decoder. Based upon the input lines, one of the output will be enabled. Now coming to the interface decoder, which we are based upon the lines A15, A0 and BHE bar. When A15, A0, BHE bar are 000, Y0 will be enabled. For 001, Y1 will be enabled, like this 111, Y7 will be enabled. So now based upon these output lines which are active, for the combination A15, A0, BHE bar, for different combinations we already discussed, either it is byte transfer from even address or odd address or word transfer from both even address and odd address. So based upon that line, these Y0 to Y7 signals will be used for enabling the corresponding memory chips. Now combining the memory chips which are selected based upon the lines A15, A0, BHE bar, 000, this combination, when A15 is 0, it indicates we are going to select the RAM blocks, which we are going to be considered as this enable signal as chip select 1, this is chip select 2, the ROM block B3 as chip select 3 and this one is chip select 4. So now we will say which memory banks are enabled. As A15, A0, BHE bar are possessing 000, it indicates it is a word transfer from both even and odd address. As it is corresponding to RAM, we are going to select both memory chips, that is CS3 and CS4. For 001 combination, it is a 8-bit data transfer from even address, that is CS4 will be selected. For 010 corresponds to odd address memory bank corresponding to a RAM, which is CS3. Next 100 combination, which is a 16-bit data transfer corresponding to a ROM. So it will enable both chips 1 and 2. For 101 combination, which is a 8-bit transfer from even address on the lines D0 to D7. So we are going to be select the chips which is CS2. For 110 combination, it is a 8-bit transfer from odd address which is on the upper lines, that is D8 to D15. Then we are going to select chip select 1. Now here, for enabling the chip select 1. If you observe the table, the chip select 1 will be enabled 2 times. If the combination on A15 A0 BHE bar as 100 or 110. In any one of the case, the chip select 1 we have to enable. So this is a OR operation, and the decoder output, which is Y4 and Y6, will be used for enabling the chip select 1. Next, for enabling the chip select 2, two times we are having two cases, we are going to be use the chip select 2 or block 2 corresponding to ROM for the combination 100 and 101. These two combinations we are going to enable the chip select 2. So the chip select will be enabled whenever the decoder output Y4 is active or Y5 is active. Next, the chip select 3. The chip select 3 is corresponding to the RAM at odd address. The chip select 3 will be enabled for any one of the two cases when A15 to A0 BHE bar is possessing 000 or 010. That means the chip select 3 will be enabled for the combination Y0 or Y2. For any one of these cases, the chip select 3 will be enabled. Now coming to a chip select 4, the chip select 4 will be enabled for two cases. One is A15 A0 and BHE bar as 000 or A15 A0 BHE bar as 001. So in that case, the chip select will be enabled. So the output lines of the decoder, whenever Y0 or Y1 are active, we are going to select the chip select 4. Now we will see the total interface diagram which are required for interfacing the given ROM and RAM blocks. The first block is a decoder which will enable the output signals which are necessary for enabling the one of the memory chips. The input lines we are going to selected with A15, A0 and BHE bar. These lines will enable one of the output lines Y0 to Y7. The chip select 1 we are going to be enabled for Y4 or Y6. Y4 or Y6, this is a OR gate. Whereas chip select 2 will be enabled for Y4 and Y5. Chip select 3 will be enabled for Y0 and Y2. Chip select 4 will be enabled for Y0 or Y1. These outputs, the CS1, CS2, CS3, CS4 will be added to the corresponding chip select lines of these four memory blocks. So here we have two 16K by 8 ROMs, two 8K by 8 RAMs. As it is ROM, we have only read permissions. As it is RAM, we have both read and write permissions. And these are used for address lines. And this is the data bus, that is D15 to D0. The address lines which we require here, we are going to take from A14 to A1, because A0 is used for selecting even address or odd address. For each 16K, we require 2 to the power of 4 into 2 to the power of 10, which is 2 to the power of 14. 14 address lines are required. That will be taken from A1 to A14. Similarly for 16K by 8 ROM. Corresponding to RAM, as it is 8K, the number of address lines are required are 2 power 13. That is 13 address lines are required. So here the address lines from A13 to A1 we are going to take for accessing any one of the RAM memory location. However, A0 is used for differentiating either it is even address bank or odd address bank. So this is the total interfacing circuit of two 16K by 8 RAM chips and two 8K by 8 RAM chips with 8086 processor. The references are AKRE, KM Burchandi, Advanced Microprocessor and Peripherals, Tata McGraw-Hill publication, second edition, 2006 I am referring. Any edition by these two authors you can refer. Thank you all. If you have any queries, you can put in the comment section. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.